Okay. Okay, welcome to class, guys. Last time I talked about adjusted R-square, right? And I showed you that what is the difference between ordinary R-square and adjusted R-square. And I proved that adjusted R-square can go negative. Okay, you should know how to calculate. Of course, in the exam, I'm gonna give you the formula. And let's continue next one. So we need to use adjusted R-square to choose between non-nested models. So what does non-nested mean? Two models are non-nested when neither is a special case of the other. Okay, so let me show you. Let me show you the example. What is a nested example? So suppose we have y equal beta 0 plus beta 1 x plus mu versus another one, y equal beta 0 plus beta 1 x plus beta 2 x squared plus mu. Okay, for those two models, okay, basically if we set beta 2 equals 0, this is our model 1. This is model 2. Okay, if we set beta 2 equals 0 in model 2, and what will you get? Beta 2 equals 0, that means this one disappear. So you get exactly model 1, right? Y equal beta 0 plus beta 1 x plus mu. In this case, okay, you get model 1. In this case, you say that model 1 is nested inside model 2. Okay, so those two are nested example. So for nested model, we need to use F-test to choose which model. So basically, this slide talk about non-nested. Okay, so this, which is the opposite of nested model. So let's take a look here. You see, models are non-nested if neither model is a special case of the other, which means you cannot get one from the other. So here we have the first one. Beta 0 plus beta 1 log cell plus mu. And model 2, beta 0 plus beta 1 cells plus beta 2 cells squared. You should be familiar with this model. This is model 1, this is model 2. You see those two, we have cells squared and also log cells. Those two are non-nested. So for those non-nested models, how do we choose? Okay, the AC, I don't know, maybe the AC is taking a rest, and right now the classroom is so quiet. Okay, so here, how do we choose? So basically here, we not by comparing the row R square, okay? We don't compare the row R square because basically model 2 has more parameters. Like I told you before, right? More parameters. As long as you plug in more x, you will get a higher R squared. I mean the ordinary R squared. So in this case, we cannot compare those models with normal R square. Instead, we compare adjusted R square. Okay, that's why I introduced you adjusted R square before. Okay, so let's compare those two models by adjusted R square. Take a look here. The first one, model 2 has 0.09. Model 1 adjusted R square, which is 0.03. Basically, which one you're going to choose? Model 1 or 2, compare the adjusted square, okay? Exactly 2, because 0.09 is greater than 0.03. Okay, so model 2 still wins, even after correcting for the extra parameter. So this isn't just because it has more variables, it's a genuinely better fit. Maybe because of the quadratic term. Okay, so I explained to you here. It's unfair to compare those kind of model by the R square, okay, which is unfair. So instead, we use the adjusted one, and obviously the quadratic model is preferred, right? So which is model 2. Next one. Okay, so this is the example, CEO compensation and firm performance. You should be very be familiar with the models that I showed you in my teaching slide, okay? So the important warning is that R square has a hard limit. It can't compare models with different dependent variable, right? So let's see the example here. One with salary, another one with log salary. Okay, this is L means log. And you see the dependent variable, this one is the original sales, right? But here is the log sales, right? So let's see the first model, model 1. What is the adjusted R square? 0.02. And you see the row R square, which is 0.029. What is the SST? Extremely large, right? About 391 million. But model 2, if we take logs, what is the SST here? Just 66.72, right? So basically, if we only look at the SST, we're gonna choose model 2 because model 2 fits way better, but this is wrong, okay? Because if you only make a decision by SST is completely different between them. One is much higher versus 67. Raw salary has huge variance, okay? That's why we get SST way too bigger. Because the raw salary data here raw salary has huge variance. And on the contrary, log salary compressed it a lot. R square measures the share of variance explained, right? Remember, R square measures the share of variance explained, but if the two y's start with total different amount of variance, the R square aren't measuring the same thing anymore. It's like comparing percentage of a mountain climbed to percent of a hill climbed. Okay, you just compare a hill to a mountain. The same word, but different scale. Okay, different scale. Because log salary, of course, with less variance. Right, so the rule is that never compare R squared or adjusted R squared across models with different dependent variable. Because they are just apples and oranges, okay? You cannot compare them directly. Even if one is just a transformation of the other. You see here, sales will transform to log sales, salary will transform to log salary, okay? Different transformation means different models. Okay, this is the warning for you. You can actually control for too many variables. The first example, okay, so this is the first example. We regression traffic fatalities on beer taxis. Okay, so here traffic fatalities on beer taxis. Don't also control for beer consumption. Why? Because consumption is the channel through which tax works. If the tax rises, because tax rises price, right? Which lowers the consumption of beer and of course lower the fatalities. So we need to control for consumption and you observe the very effect you are trying to measure. The tax coefficient would only capture what's left over, not the real policy effect. The next example is about family health spending on pesticide exposure. Don't control for doctor visits. Okay, don't control for doctor visits. Why? The same logic. Doctor visits are likely a consequence of exposure. If you get affected by pesticide, of course, you're going to go to see the doctor, right? So doctor visits are likely a consequence of exposure, part of the mechanism, not something to hold fixed. So the general rule is don't control for variables that are themselves outcomes of your key X. You'd be blocking the very effect you want to estimate. Okay, don't control for variables that are outcomes of your X. One more point. Purpose matters, okay? So let's see here. In a house price regression, include price assessments. If you are testing whether assessments are accurate, exclude them if you are just explaining what drives house prices since assessments are downstream of the same underlying factor. So the takeaway is, before controlling for a variable, ask, is this a cause of X or a consequence of X? Controlling for consequences kills the effect you are trying to measure. So this is the key point. When you run your regression, you should have control variable, right? Control variables. So the question you should ask is, before you control a variable X, you should ask yourself, is this a cause of X? Or is it a consequence of your other X? If you control for consequence, it kills the effect you are trying to measure. Okay, let's continue here. So now is the flip side. Sometimes adding variables help. So there's a trade-off, right? Adding a variable can worsen multicollinearity, but it can also reduce the error variance. Still remember that sigma square shrinks as we explain more of why. Okay, so the best case is that you add a variable that's uncorrelated with your existing regressors, okay? So you should add that one, and you get the error variance benefit without the multicollinearity cost, which is the pure one. But the problem is that perfect uncorrelated variables are hard to find in practice. Makes sense, right? Nowadays, each subject is multidisciplinary. You cannot only explain one subject by itself, like when you explain economics, you need to incorporate with political science. What else? Environmental, right? So in practice, perfectly uncorrelated variables are hard to find. Okay, keep that in mind. So here I showed you example. Think about this one. We regress the individual beer consumption on beer price. Adding individual characteristics. What do we have for individual characteristics? For example, age, income. Okay, those are individual characteristics. And of course, age, income, especially age, and also gender, right? They are qualitative data. They are not numbers. They are female, male, what is your age, and age, discrete variable. So basically, if you can add individual characters, suppose you want to investigate the beer consumption, it helps. But the problem is that you need to collect the data, maybe sometimes by yourself, okay? So here, if we add individual characteristics of it will make the price elasticity estimate more precise. Why? Because they soak up leftover variance without being correlated with price itself. So when deciding whether to add a control, weigh the multi-collinearity cost against the precision gain. Variables uncorrelated with your key X are the ideal free additions, okay? So uncorrelated with your key X is very important. Next one, do you still remember that predicting Y is much harder than predicting log Y? Okay, let's go back to the first slide. Here, it's hard to reverse the log operation when constructing prediction. So here, I'm gonna show you why is that. Look at this, a lot of equations. I just record you that we can't just exponentiate a log prediction to get Y back. Right? Basically, what is the inverse function of log Y? If we want to get Y, we just take the exponentiate, right? Mathematically, yes. But this one is biased. Okay, this one is wrong. Why? Let me show you. Let me show you why and how to fix it. Suppose here we have our regression, which is log Y, okay? Equal beta 0 all the way through to beta kxk. And let's exponentiate both sides. You get Y equal exponentiate of the other and also exponentiate of mu. But the problem is that if we just plug in and exponentiate, we are ignoring exponentiate of mu. And exponentiate, okay, so if we take the expectation of exponentiate of mu, this one doesn't not equal 1. Okay? Even though expected mu equal 0. Even expected mu equals 0, but expected exponentiate mu doesn't equal 1. Okay? Because exponentiating is nonlinear, so this matters. In fact, this is always underestimate the true value, okay? So here we need Jensen's inequality. Have you heard this before, Jensen's inequality? Because exponentiate function curve upward. So the average of exponentiate mu is always bigger than exponentiate of average of mu. Let me try to write it down. So what is the problem here? Because exponentiate function curves upward. So the average of expected mu is always bigger than the exponent of average of mu. And also the exponent average of mu equal 1. Okay, this is the problem. So how do we fix it? Okay, so here we're gonna fix it in 3 steps. The first one, back transform the linear part. Okay, so we're gonna transform the linear part as usual because this is the linear part. This alone gives you the median, not the mean. Okay. So this linear part will give you median, not the mean. And then we need to estimate the missing pieces, which is the smearing factor. This one. 1/n times summation of exponent mu I hat. So you need to know this is the smearing factor. Okay, so let's use alpha hat to represent. So this is the average of exponented residuals. So let's see, what is the step? The first step, we're gonna back transform the linear part, okay? And then we need to multiply the smearing factor, which is our alpha hat here. And then we multiply them together, which is here. This is the linear part. And then we multiply the smearing factor. So we can get the y hat. So this is exactly the prediction for y. Okay, this is the prediction for y. Clear about those 3 steps? So basically y hat equals the linear part exponent from beta 0 hat all the way through to beta k xk hat. And then we need to multiply the alpha hat, which is the smearing factor. Okay, so this is the idea. You don't have to remember all the derivative mathematical proof, but you need to know the idea. How can we predict y correctly? It's not just like, okay, so basically we take log y, but in order to get y, you cannot just take the exponent. You have to multiply the smearing factor. Okay, just keep that in mind. Let me give you one example. Suppose our predicted log wage. Okay, so log wage equal 3.5. So this is our predicted log wage, right? So the simple way, if we exponent 3.5, what do you get? Can you use your calculator? Okay, so in the exam, you can use your scientific calculator, okay? But only calculator. You cannot take any other notes. For sure, okay. So the rule is that if you cheat in the exam, you get failed for sure, 100%, and you get the penalty, which is a 1 semester probation. But if you don't cheat, you try by yourself, okay, you will pass maybe with lower grade. So you need to think about it. So please tell me, what is the exponentiate of 3.5? What is the answer? How much? Yes, just take exponentiate of 3.5. Can we do that? I think yes. I didn't get that. Can you get that? But let me give you the final answer. So if we take the exponentiate for 3.5, which is $33.12 per hour. But this is wrong, right? This is wrong. Instead, we need to use the smearing factor. So here, suppose the smearing factor is 1.15. So the corrected one is you use the exponentiate 3.5 times the smearing factor, which is okay. So you see the difference. The naive guess was 4.97 too low, which is underestimated. Okay, so the point is that never just exponentiate the fitted log variance. It always underestimates. Multiply by the smearing factor to correct for this. Okay, the last slide. Example again. Now let's finally solve the problem from before. Using the correction we just learned, we can do a fair R squared comparison between a logged and unlogged model. Okay, model 1, what is the R square? 0.201. Model 2, what is the R square? 0.24. Sorry, the row R square is 0.318, right? But that's the R squares for predicting log Y, not salary itself. Still not comparable. So the trick is use the smearing correction from last slide to convert model 2's prediction back into actual salary dollar, then compute R squares from those predictions against actual salary. That gives us R square tilde, okay? This, we got it from smearing correction. This is not adjusted R square, okay? This is R squared tilde. This is after smearing correction. Because you see here, this one, Model 1, salary. So this R square is for salary. But for model 2, this is log salary. So the R square here is for log salary. But basically, we want to compare salary dollars. That's why we need to use the spelling correction. So we get R squared tilde. Okay, so right now we can compare those two. So basically, right now, those two R squared, they measure the same thing, which means how well each model predicts salary in dollars. Finally, comparable. Okay, and the conclusion is this one is bigger than this one, right? 243 is bigger than 201. So the log transformation is genuinely better, not just an illusion from different scales. Okay, so the takeaway, to compare a logged and unlogged model, convert predictions back to the same unit first, and then we compare R squared. So let me write it down here. Right now, both R squares can be directly compared because right now both R square, they are using the same units, right? Salary dollars. Okay, so I finished chapter 4.2 now. Can you summarize? Can you discuss with your friends? Summarize what does chapter 4.2 cover about? So midterm exam covers chapter 1 to chapter 3. Chapter 3, we have two sub-chapters, okay, 4.1 and 4.2. 4? Yes, 1 to 4. Okay, I think I need to do the Kahoot now, otherwise I don't have time. Okay, get your phone ready. Extra point. Start. So chapter 2, 3, 4, 10 questions each. I'm gonna stop recording because I'm gonna send